Okay, in this lecture, we are going to, this is the overview of the 12th chapter of the book. And this deals with network models. Network models is a very important mathematical framework that we kind of understand how things are connected. Things can be people, things can be links on the internet, things can be cells in a metabolism. They can be anything that we kind of look for connections. This kind of originally, historically, this came out in the connection is this famous historical problem of Königsberg. I don't remember. I think it's Switzerland. I'm not sure. It's written in the caption of the first figure of the lecture notes. And you see that here in this little town, there are bridges, right? And it was a question or a puzzle in the beginning, whether you could go to every part of the bridge and go through every bridge only once. And this was a problem or a puzzle people have struggled. This is a problem that goes back to 17th century. But at the end, the answer was no, it was not possible. But it was a mathematician who modeled this kind of city, little town, with kind of these lands, pieces of these lands as nodes, and then these bridges as edges. And they kind of modeled this environment with a mathematical network model, and kind of got from there the answer that was not possible. See now, not working. Now it's working. Okay, so a lot of complex systems can be modeled very effectively using networks. For example, an example of this is a citation network. Right? Who cited which paper, who cited which paper in the citation environment. Of course, this is a network that is directed, right? One paper that cites the other doesn't necessarily mean that the other paper cites the other one back as well. This is actually a little bit directional with the timeline. You cannot really cite a paper that is coming 1 year in the future because it doesn't exist yet. Sometimes articles exist on archive, they kind of cite each other, even if it looks like on paper they were published later. They had been citing an archive version, but most often they only cite papers that are in the past. And another example is the links between websites, right? Links on the web that are kind of from which link people go to which link, kind of. This is a big network as well. Another example here is this is a study that is this was done in a school in the US. So people asked, who are your friends in the school, to children, and children answered, for example, Mike is my friend, Rob is my friend, John is my friend, these kind of things, and they created a network. You see that they kind of demonstrated this large clustering between different kind of black and white people, and other. You see that there is a significant clustering between the friendship, not only between in black and white. Also, for example, the black students were kind of grouped up here, some of them and some of them. Of course, there are cross links, but you see really the behavior. So it's really important to mathematically model these kind of connections between people, between links, between cells in a society. Anything you can think of, or I don't know, social connections, social media connections. All of these are modeled with networks. So what we kind of introduce a very simple network now to understand what is the idea behind the mathematical model. So here is a network, flight connections between cities. This we can represent with a network, right? Let's assume we consider only 3 cities, Paris, Berlin, Vienna. Okay, and then Paris, Berlin, Vienna. And we can model this with an array that is 3 by 3. If there is a connection between Paris and Berlin, we put 1 here, flight connection. If not, if there is not a direct flight, then we put 0 here. Okay, and this is a good representation. Of course, this is a binary array, right? This is a binary network. We kind of, if we have a connection, we don't really care about how strong, how many flights per day or something like that. If we have a connection, we put 1. This is the simplest thing we can think of or model. And it's also symmetric. So we don't really check if there is both ways or something. We assume that if there is a connection, flights are arranged in both ways. Okay. So here are some important parameters that we can look at these kind of things. Here, these cities are considered as nodes in my network. And these connections are named as edges. And we can kind of calculate a very important parameter for each node, that is the degree. Degree means that how many edges are connected to each node. So in this example, Paris has 2 degree of 2. Why? Because if I sum this row, which gives me how many cities Paris is connected to, right? And that is 2. And Berlin is only 1. Vienna is only 1, right? This means that Paris is actually better connected than the other 2. Is this clear? In fact, if you want to go from Berlin to Vienna, you can't really go this way. You have to go to Paris first and then go to Vienna, right? So kind of this gives you an idea about the connectivity. And of course, this is a network that is connected. What does it mean? That overall, there are no edges that are isolated. For example, if this was 0, the Vienna would be an isolated disconnect. This would be a disconnected network, right? There would be no way to reach Vienna from outside. So there are no isolated nodes. This is important. So it is possible to go from each node to each node through edges. This is important. This defines connectedness. And connectivity is the number of elements removed to create isolation. For example, here, if I remove Paris, what would happen? As a node and its connections, the network disappears, right? Because here, without Paris, it's 0, 0, 0, 0. There is no connection left. So the connectedness goes down. Of course, if we have a lot more nodes, this would be a different. But for this particular network, its connectivity is 1. Because if I remove Paris, we created isolation in the network. Is this clear? This is a number of. Of course, there are a lot of different kinds of graphs and different kinds of models that how we can introduce a graph and how we can model different kind of graphs. And especially if we are going to introduce a random of our own, how we are going to initialize it is a problem. One approach is called Erdos-Renyi random graph. And here we kind of create a number of nodes and then connect each node, each couple nodes with a probability of small probability of P. And then we kind of get this kind of random looking network. And this is the kind of overall behavior and a degree distribution. This is the theoretical degree distribution. It's a binomial. The formula is found in the lecture notes. I won't review here, but you see that the simulated number of nodes for this particular example. Of course, these numbers, these fluctuations may change each time you realize the network from scratch, but it will mostly, and the larger the network is, the better fitting it would be to the theory, because the probability deviations will get smaller and smaller. Another model is the small world model, small world graphs. And here we assume that each node is connected to like a C number of nearest elements. In this case here, the C is 4. This model has 2 important parameters. One is C, how many neighbors it's connected to each node initially, and then P. P is that once I generate this network, that I connect each node to 4 nearest neighbors for this case, because my C is 4, and I do rewire each node with a probability P, small probability. So kind of these rewiring probabilities decreases the distance or the path lengths. Path length is defined by the distance. What is the shortest number of edges I have to go through, for example, to reach from this node to this node, right? For example, in this case, I have to go through like this to this node. But if there is a rewiring, I can just go here and then here. Distance is greatly reduced. And another model is called the preferential growth. This is kind of a model that we kind of we start with a small number of nodes here in the beginning of the network, and then when we keep adding nodes to the network, and whenever there is a parameter m, how many edges I assign to each new node, and I connect them to a node that is proportional to their degree. So if a node has higher degree, it becomes more likely to be connected to a new node. But as a result, this happens. This shows a power law in the degree distribution. This is something that we demonstrated before. This is a probability. This is a complementary cumulative distribution function, and this is the degree of nodes. And you see that this very similar behavior as I was demonstrating also in, for example, forest fires, the fire size distribution. And of course, there are important cases. For example, here, what is the, let's say this is a network. What is the connectivity of this network? One, because if I cut this node, or actually connectivity is about removing a node. If I remove D, what happens? The network becomes disconnected, right? These two become isolated.
This is enough, but you can't reach one node from any other node. Not connected.
Yes. So one node or a group of nodes. For example, if I remove D, this will be disconnected. But if I remove F, no one cares. It's still connected. If I remove G, it's fine. But for example, this node and this node are, I mean, if I remove any of them, the network will become disconnected. This means that its connectivity is 1. And also, there are these kind of edges that are more important than the others. Why? Because here, if I remove this edge, the network is still connected, right? But if I remove this edge, this part becomes isolated. The same with this edge. If I remove this edge, the network becomes disconnected. So these edges are kind of become more important than the rest of the edges. Yeah, this is important. They are usually, these bridges are usually signs for weak points or bottlenecks in these kind of networks. And you see here, this is a review paper, but here is represented very well that this is the average distance from each node to each node, average distance between nodes in a network, in a very large network. And this is the fraction of edges that are removed. Well, how is the distance changing as a function of removed nodes from the network? The blue squares are the ones that I choose nodes randomly and eliminate them. How is the distance changing, average distance between nodes? You see that in a very large network, it doesn't change at all. If I remove one network, they will find their way through another network and the distance won't change much. But the orange, not the orange, the red circles are the ones that when I remove nodes with the order of degrees, I kind of remove highest degree nodes first. In this case, you see that it's dramatically affected by the number of vertices removed. As soon as I remove only 2 elements, it is the distance is affected a lot more than if I remove half of them, maybe with randomly. Not half of them, I mean 5% of them. Is this clear? Okay. So so now one way to represent the network mathematically is what I call this matrix, is the adjacency matrix, we name it. And this matrix represents an n by n array that is indicating the connection. If it's not binary, it might mean the strength of the connection or length, for example, for roads, or it might also be asymmetric. Here it's symmetric. For example, what is the example of a symmetric network? Bridges, yes. If a bridge exists between 2 parts of a town, it goes both ways, right?
It's not one way.
If it's not a one-way bridge, there are a lot of streets that are one way. But if we assume that it's possible to drive both ways, it is an example of a symmetric or wired connections. If there is a connection between 2 points in an electric circuit, they are connected kind of, and electron can kind of travel in both ways, unless there are diodes in the circuit, right? And what is the example of an asymmetric network?
With one way.
Yes. Or for example, the citation network is asymmetric. An article citing another one doesn't necessarily mean the other one has to cite the other one as well. So, but the simplest thing we can think of is a symmetric binary adjacency matrix that is represented here. You see that if two cities are connected, it's 1. If they're not connected, it's 0. So this is a very useful kind of mathematical tool. Why? Because I will show you in a moment. This is the square of the adjacency matrix. If I matrix multiply this by itself, and I get this. Okay. So, what does this element represent? Okay. This is what happens is that when I calculate a square, I multiply this row by this column and sum them up and write it here, right? And if you think about it a little bit, this is actually how many ways, the number of ways, possible different paths I can take from Paris to Paris. Okay? Which is indicated because if you think about all the different parts of this equation, this first element is Paris to Paris, right, of a square. And how I mathematically calculate this from Paris to Paris through, I multiply this number by this number, which means that can I go from Paris to Paris through Paris? The answer is no, because I cannot fly from Paris to Paris. And then plus I multiply this number by, wait, A1 to, I'm becoming confused now. Yeah, can I fly from Paris to Berlin and then from Berlin to Paris, right? Which means that can I go from Paris to Paris through Berlin? Yes, and the Vienna also yes. This gives me the number how many ways I can go from Paris to Paris. This is a very useful actually. And let's take another one. For example, this one is this is the, how do I get this number when I make matrix multiplication of this by itself? I multiply this row and this column, right? If you just have a look at how I operate this array, it's very easy to see in such a small kind of adjacency matrix. Actually, realize this is actually from Vienna to Berlin, right? And how many ways is possible is, you see here, the options are when I multiply different elements of this is through Paris or through Berlin or again through Vienna. And you see here that only this one gives me 1 and this is added as 1 only. So there is only one way to go from Vienna to Berlin. Yes.
But is this only with one stop? Like, because you could go from
Yes.
Vienna to Paris and from Paris to Berlin.
Yes. Yes. That is if you take the A cubed.
Yeah.
Okay. If you take do a matrix multiplication with A cube, you will find out how many ways is there possible to go from, for example, Paris to Vienna with 3 flights. This gives me how many possible ways with 1 flight. How many possible ways with 2 flights? If I take the other cube, how many possible ways to 3 flights? Of course, what does this mean? I can keep taking the power of this adjacency matrix and try to see in how many steps 2 cities get connected. I can use this method to calculate the path lengths between the nodes, right? I can calculate a lot of different things. Is this clear? For example, I can initiate an array with path lengths that are infinite in the beginning. I assume I can numerically represent this number with a -1 or something like that. And I start with length 1. How many cities have length 1 between each other, right? These ones. that are connected from length 1. And after one step, for example, Paris is connected to Paris with 2 steps, and these are 1 step. So most of the path lengths are 1 or 2 for this case. I register kind of these ones in the beginning in the path length, and then the ones that are not 1 here, the ones that are now non-zero here in this one, I register these distances as 2. So the path length for this adjacency matrix would be 1, 1, 1, 1, 2, 2, 2, 2, 2. Why? Because all the elements are now connected. So after taking a square, I can go from anywhere to anywhere. It would not be like this if I had more elements. Then I keep taking the power of the adjacency matrix and try to look for a new way if there is introduced. Of course, so this is the important a to power j. Now we have shown that this is the number of ways to connect from node I to j in t steps. Okay. And of course, now this gives me the number of triangles. This is the trace of the a cubed. Why? Because the diagonal of a cubed gives me how I can go from one edge to the same edge in 3 steps, right? Is this correct? You understand this, right? This gives me the number of triangles if I take the sum of the diagonals of this array. Is this clear? However, I count every triangle this way 6 times. Why? Because I count every triangle, I can go this way or the other way. I can complete a triangle by like this or like this. I count 2 times, and I count each triangle from each node 3 times from there as well. So I count excessively 6 times each triangle. So I kind of can calculate immediately the number of triangles in a network using the adjacency matrix really effectively. And this is the 6 is coming from the direction and the number of nodes. Okay, so what are the advantages of representing a network within a adjacency matrix? The pros are simpler algebra and algorithms, especially if we work with MATLAB, Python, these kind of programming languages that like matrix operations. We just keep taking the power of the matrix and find everything we need. Of course, this is efficient for dense graphs. If we have a lot of edges if the network is very much connected, we have a lot of edges, right? It's not really inefficient to represent this, and we have a very rapid access to specific edge. If I want to check it, if there is a connection between 2 nodes, I can immediately find it because it's in my array. I have it already. So it is good for these kind of networks. Here, every white pixel is a connection and every black is a disconnection. But what are the cons? Of course, it requires more space for larger networks. If I have 10,000 nodes, I have a 10,000 by 10,000 array, right? It's not efficient for sparse graphs. Sparse graphs means that we have only a few edges that connect. If I have such a network, let's say I have a network with 10,000, or even sometimes networks are bigger. Think about the larger networks, for example, electric circuits in a whole country, the electric units or the trafos that are connected to each other. Very few edges, but there is a lot of nodes. This I need, for example, here a 100,000 by 100,000 array. Instead, if I have fewer nodes, I can just keep a list of nodes, right? It would be more efficient to store the information. So here we can also introduce another way of keeping the information, all the information of a network, that is the adjacency lists instead of a matrix. Here, what we keep is that we kind of take what are the connections that each node have. Here, how many edges are in this network actually? 2, right? Paris is connected to Berlin, that is one edge. Paris is connected to Vienna, that is another edge. I have only 2 edges, right? So I can just keep an edge PB, PB. I kind of indicate this doesn't have to be letters, they can be numbers, right? If I numbered the cities 0, 1, 2, blah, blah, blah. So I kind of keep a list. This is 2 by 2, right? Because I have 2 edges and I have 2 elements. I mean, usually if I have n edges, this will be an m by 2 array, kind of. Is this clear? So depending on the structure of a network, of course, this requires less space for larger networks. It's very efficient for sparse graphs if we don't have a lot of connections. And if we have an algorithm that is iterating over the edges, if we are looking for something in a network, this is more efficient. Of course, we have a very small access to a specific edge because we have an array of m by 2. But if I really want to look for if the 2 edges are connected, I have to really go through the lists and try to look for the specific edge if that exists in the array. So I can kind of make a numerical effort to find it. And it's also not efficient for these kind of well-connected graphs. Is this clear? But in general, as long as the networks are large, specifically more than 10,000 nodes, it becomes, if they're not very well connected, it becomes more effective to store the number of edges instead, because the adjacency array becomes bigger and bigger, especially if you just want to save the network to a file. And of course, you can easily write a function to transform from one representation to the other. I believe actually there are easily found functions that are already built in MATLAB and Python, but I don't really know. I would just write on my own. It wouldn't take so much time. And also this slide came in an earlier lecture about forest fires. We can, if we want to check connectedness between nodes, we can make, of course, if we want to check connectedness between all the nodes, and we don't really care about so much time, we just want to program something faster, we can use the powers of the adjacency matrix, as I told you. But if you care about the specific node or specific kind of connections between edges, you can kind of search through connected edges of a node. And this can be done in 2 different ways. This is the breadth first search. So you kind of go from the first elements to all the nodes that have distance 1 to this, right? And then here the numbers are associated with the order of the search. You kind of go from here like this, and then go to this, and then go to this. The depth first search is kind of you pick one neighbor, and then you keep going, pick another neighbor, and then when there is no neighbor, you go back here, pick another neighbor, you go back here, pick another neighbor, like this. This takes less steps because you take all of these at one step, another step, but this needs more memory needs. So it's depending really on the specific target you have, that the network you're dealing with. This has more steps, but this is less memory consuming, obviously, because at the time you only regard a list you have already gone through, and then you just have to check one element at a time. Of course, these don't really seem to make a big difference when I'm showing you an example of a network with 10 edges, 10 nodes. But it will make a huge difference if you are dealing with a network that has 100,000 nodes. And of course, there are different kind of networks that have, for example, this one has weighted adjacency matrix, which means that it's still symmetric, but the elements of the adjacency matrix are not 1 or 0 only. So in this kind of networks, this kind of edges might represent, for example, how many bridges exist between Gothenburg and Hisingen, for example. This can be, or different cities of Sweden, or different islands, for example. You can assume this one is the number of bridges. And depending on the adjacency matrix property of the network you are defining, this can be like kind of connections or the distance. You can also represent, for example, what is the distance? Then the higher the number means the less the connectivity in that case. So there are 2 different kind of representations you need to be careful about. It doesn't always mean that, for example, if it's a distance matrix, then it might be meaning different. So you see here in binary graphs, if it's 1, it's a good connection. If it's 0, it's not a good connection. But it's in weighted graphs, the larger number of in the adjacency matrix might refer to better or poorer connection, depending on what you are defining with the adjacency matrix. And shortest path here doesn't need to be always the smaller number of edges visited. You understand this? Because there might be a direct connection, for example, from I don't know, Gothenburg to Helsingör with a car one way. You can take it, but a shorter might be through Helsingborg, for example. Okay, this was the last slide. Is there any questions about network models? Is everything clear? How many of you have done disease spreading for this? 2. How many of you have done network models? You, what did you do? Okay. I mean, this is, I mean, network models, if you don't have a background, you can really read this chapter. Is I myself don't have a very strong background on these network models. And yeah, I kind of read the literature for writing the chapter, actually. So it's really not that difficult to grasp all these things. And it's very helpful to understand because it is used to model a lot of different things. It's a powerful theory. Does a to power t represent anything for this case? Aaron was asking. In this kind of example, a to power t, I'm actually not sure. It might represent something, but not at all obvious to me that, like in the binary cases. Because if you take the square of this, you multiply elements. No, it really depends on the array, but I don't think you can make a general assumption like in the case of binary arrays. In the case of binary arrays with an adjacency matrix, but what you can absolutely do is that you can still convert this to a binary array and then take the powers, and you can see in how many ways, how many steps. If this kind of represents connectedness, and then you can kind of understand the idea. So you can still make this binary and take the power of it and try to calculate. Depends really on the structure of the array.
Could you take the power and then just look at non-zero elements? That should still mean that they are connected. If we
yes.
If we don't pay attention to the value, just if it's zero.
Yes, I guess so, actually.
Because you don't have that final size.
No. No, you can take the power of this. It would actually still give you the connectedness if the two edges are, but I don't really know what does the number mean.
No, I just
Yeah.
thought that if it's non-zero.
But I'm pretty sure someone has, I mean, network models is something like each article that is in the list of the references in this lecture notes is cited easily more than 10,000 times, or I don't know, a few thousands. So it's really like a very, very widely studied topic by mathematicians and everything. You see the analysis methods in the lecture notes about all these path lengths, clustering coefficient, all these different things. They kind of made the theory for everything, kind of. So I am pretty sure this means something. And you can, but this review paper is actually a very, let me see. Oops. This review paper is from Newman. I can highly recommend to have a look. It's a very nice paper about overviewing the network models and giving the background information, and really nice overview of the theory of the adjacency matrix and a lot of other literature as well. And I mean, this is one of the most cited people on Earth, after like a few people like Einstein and stuff. I mean, I think this guy has over 50,000, 60,000 citations. I don't know the really number, but it's really like a very he has very well known a lot of papers. Okay, if there is no more questions, I will conclude the lecture here. Thank you, and I will upload them on YouTube, but maybe not as fast, maybe evening tomorrow. Okay, then see you next Tuesday.